Imagine holding a crystal in your hand and watching light scatter through it, splitting into colors because of an invisible order, an arrangement of atoms so precise that it dictates how reality itself interacts with it. Now take that idea and stretch it beyond space, beyond structure, into something far stranger. A crystal that doesn't repeat in space, but in time. This is not science fiction, and it's not metaphor. It's a real physical phenomenon first proposed by Frank Wilczek, a Nobel Prize-winning physicist who asked a deceptively simple question. What if a system could exhibit order not just in where things are, but in when things happen? What if, instead of a repeating pattern in space, you had a repeating pattern in time? Motion that never stops, not because energy is constantly being fed into it, but because the system itself exists in a state where repetition is its natural condition. This idea became known as a time crystal, and for years it lived at the edge of theoretical physics, a concept that seemed to flirt dangerously with the idea of perpetual motion. But this wasn't the classical perpetual motion that violates thermodynamics. Time crystals obey the laws of physics very strictly. They do not create energy. They do not extract work from nothing. Instead, they live in their lowest possible energy state, a ground state, and yet somehow they continue to move. It sounds contradictory, almost paradoxical, because we are used to thinking of motion as something that requires energy. A spinning wheel slows down unless something keeps pushing it. A swinging pendulum eventually stops. But a time crystal doesn't behave like that. Its motion is not something added to it. It is part of what it is. In 2016, this idea crossed the threshold from theory into reality when scientists managed to create the first experimental time crystals in controlled quantum systems. These were not large, visible crystals like quartz or diamond, but microscopic arrangements of quantum particles carefully engineered to exhibit this strange temporal order. And even then, the phenomenon remained fragile, isolated, and difficult to manipulate, because there was a fundamental limitation, one that seemed almost philosophical. The moment you try to observe or interact with a delicate quantum system, you risk disturbing it. In the case of time crystals, this meant that connecting them to any external system, anything that could measure, influence, or use them, would destroy the very behavior that made them special. For years, that limitation defined the field. Time crystals could exist, but they were like perfectly synchronized dancers performing behind glass, untouchable, inaccessible, beautiful but impractical. And then something changed. At Aalto University, in the Department of Applied Physics, a research team led by Jerry Mackinnon decided to challenge that boundary. Their goal was not just to observe a time crystal, but to do something far more ambitious, to connect it to the outside world without breaking it. To understand what they achieved, you have to step into the strange environment where their experiment takes place, a world of extreme cold, where temperatures approach absolute zero, and matter behaves in ways that defy everyday intuition. In this frozen landscape, the researchers used a substance known as helium-3, cooled to such low temperatures that it becomes a superfluid. In this state, helium flows without friction, without viscosity, like a liquid that has forgotten how to resist motion. It is within this exotic medium that the time crystal emerges. But it doesn't begin as a crystal. First, the team injects energy into the system using radio waves. These waves don't simply heat the material. Instead, they create quasiparticles called magnons. These are not particles in the traditional sense, but collective excitations, ripples in the alignment of quantum spins that behave as if they were individual entities. Think of magnons as coordinated disturbances, like a stadium wave moving through a crowd, where each person only moves slightly, but the overall effect travels as a coherent entity. As long as the radio waves are active, the system is being driven, continuously fed with energy. But the real transformation happens when the input is switched off. At that moment, the magnons begin to organize themselves. Instead of dissipating randomly, they lock into a synchronized pattern, a rhythm that repeats in time. This is the birth of the time crystal. What's remarkable is not just that this pattern forms, but that it persists. The system continues its oscillation for an extended period, on the order of hundreds of cycles, lasting minutes, far longer than typical quantum states can maintain coherence. Eventually, the signal fades, but not because it is disrupted externally. It simply decays naturally, like an echo slowly disappearing into silence. And this is where the breakthrough happens. As the time crystal evolves, the researchers discovered that it becomes coupled to a nearby mechanical oscillator, a device that vibrates at a specific frequency, like a microscopic tuning fork. This coupling means that the time crystal is no longer isolated. It is interacting with another system, exchanging information, influencing and being influenced. For the first time, a time crystal is no longer trapped in its own closed quantum world. It is connected. This connection transforms the time crystal into something even more powerful, an optomechanical system. In physics, optomechanics studies how light, or more generally electromagnetic fields, interact with mechanical motion. These interactions are at the heart of some of the most sensitive measurement devices ever built. In fact, similar principles are used in experiments that detect gravitational waves, tiny ripples in space-time itself. These detectors rely on incredibly precise measurements of motion, where even the smallest disturbance can carry profound information. What Mackinnon and his team showed is that the behavior of the time crystal mirrors these optomechanical phenomena. Changes in the crystal's frequency correspond directly to the kind of interactions physicists already understand and use in high-precision technologies. This is not just a conceptual bridge. It's a practical one. Because once you can connect a time crystal to an external system and control its properties, adjust its frequency, influence its interaction, you can begin to think about using it. And this is where the story shifts from discovery to possibility. Time crystals have a unique advantage over many existing quantum systems: longevity. In quantum computing, one of the biggest challenges is maintaining coherence, keeping quantum states stable long enough to perform meaningful calculations or store information. Most systems lose coherence quickly, collapsing under the influence of their environment. But time crystals persist. Their oscillations endure far longer, making them natural candidates for something that quantum computing desperately needs: reliable memory. Imagine a quantum computer where information is not stored in fragile, fleeting states, but in robust, self-sustaining rhythms, where the passage of time itself becomes the storage mechanism. This is not guaranteed. It is not even immediate. But it is now conceivable in a way it wasn't before. Beyond computing, there are other implications. Time crystals could function as frequency combs, tools that provide extremely precise reference signals. These are already used in cutting-edge measurement devices, from atomic clocks to spectroscopy systems capable of detecting minute changes in matter. If time crystals can be engineered and stabilized further, they could push the sensitivity of these instruments even closer to the fundamental limits imposed by quantum mechanics. And that phrase, the quantum limit, is where the deeper significance lies. Because what this research ultimately represents is not just a new kind of material or a clever experiment, but a step toward controlling systems at the boundary where classical intuition breaks down completely. A place where motion doesn't require energy in the way we expect, where time itself can host structure, where the distinction between dynamics and stability begins to blur. We started with a simple idea, a crystal that repeats. Then we extended it into time. Now, we are beginning to connect that temporal order to the rest of the physical world. And in doing so, we are learning that time is not just a backdrop against which events unfold. Under the right conditions, it can become a dimension of structure, of rhythm, of information. A crystal, not of atoms arranged in space, but of motion arranged in time, quietly oscillating at the edge of what reality allows, waiting to be understood, and perhaps one day harnessed.